Hey everyone, oh Allah guide me and guide through me. اللهم لا سهل إلا وجعلته سهلا وجعلت الصعب إن شئت سهلا. Today in this episode we are gonna talking about the measuring instruments. Measuring instrument. First of all, the electrical measurement devices are divided into two types. Okay, electrical measurement devices divided by or divided into two types. Number one, analog measurement instruments. Number two, digital measuring instruments. We have two types for electrical measurement devices, analog and digital. The idea of operation, both of them. Number one, analog. The idea of operation depends on the torque that is generated a movable coil carrying current in the magnetic field. Again, depend on the torque that is generated on a movable coil carrying current in a magnetic field. Idea of operation to digital measuring instruments depends on the digital electronics. Okay, digital electronics. Examples for these devices: analog like galvanometer and ammeter and voltmeter. So the digital measurement like AC and DC current digital measuring instruments. Okay, AC and DC current digital measuring instruments. Method of reading. Number one, the analog depends on pointer to give the required value. Depends on pointer to give the required value. And number two, digital depends on digital number that appear on a screen to measure the value. Okay, depend on digital number that appear on a screen to measure the value. Today in this episode we are talking about galvanometer. First device we have galvanometer. Moving the coil galvanometer, as we talking about uses for any device we have. Okay, for galvanometer, indicating the existence of very weak direction current in electric current and measuring their intensities. Number two, determines the direction of weak direction current. Okay, galvanometer determines the direction and magnitude or of very weak direction current. Galvanometer deals with direction current and very weak direction current. Okay. Structure of galvanometer: a coil of thin wire is wrapped around a rectangular aluminum frame that can rotate about its axis. Okay. Number two, soft iron core in the form of stationary cylinder is placed inside the rectangular frame and isolated from it to concentrate the magnetic field inside the coil. Okay, we use soft iron core form stationary cylinder to concentrate the magnetic field inside the coil. Okay, the group is placed between the poles of a horseshoe magnetic, which are made a concave to provide a uniform radial magnetic field, so the magnetic flux density becomes constant. Okay, in this case we use the concave magnetic or like a horseshoe because provide a uniform radial magnetic field, so the magnetic flux density become constant and perpendicular to the vertical side of the rectangular coil irrespective of its position. Number four, the frame is pivoted on a gate spring to facilitate its movement. The frame is pivoted on a gate springs to facilitate its movement. Number five, a pair of spring springs serve as a current leads to the coil and to control its motion as they return the coil to its original position when the current is cut, like it's disconnected. Again, a pair of spring to serve as a current lead to the coil and to control its motion as they return the coil to its original position or fixed position or rest position when the current is cut. The current is cut, in this case disconnected. Okay. Number 6, a pointer is fixed on the coil such that they can move together either clockwise or counterclockwise direction. Again, a pointer is fixed on the coil such that they can move together either the clockwise or counterclockwise direction. As we're showing the opposite figure is the structure for galvanometer. Next, idea of working galvanometer. It depends on the torque acting on a movable coil carrying an electric current in a magnetic field. Again, it depends on the torque acting on a movable coil carrying an electric current in a magnetic field. Magnetic effect of electric current. It depends on the torque. Okay. Explanation for working galvanometer. Okay. Imagine with me when electric current passes in the coil. When electric current passes in the coil, two parallel forces are generated. Okay. Equal in magnitude and opposite in direction. Two longitudinal sides of the coil. The force produces a torque and the coil rotates around its axis. Okay. Again, when electric current passes in the coil, two parallel forces are generated, equal in magnitude and opposite in direction, at longitudinal side of the coil. The force produces a torque and the coil rotates around its axis. And the magnetic force produces a torque that rotates the coil in the clockwise or counterclockwise direction, depends on current direction. Then the torque rotates the coil in the clockwise or anti-clockwise direction, depend on the current direction. The pointer moving clockwise or anti-clockwise, it depends on. Okay, we have some notes about the galvanometer. Number 1, the zero scale on the moving coil galvanometer is in the middle. Why? Why the zero scale of galvanometer in the middle? Okay, because to determine the current direction in its coil, clockwise or anti-clockwise. Number 2, the moving coil galvanometer is not veiled for measuring the high electric current intensities. Why? Why the galvanometer is not veiled for measuring the high electric current intensities? Because the flow of electric current of high intensity may lead to a sudden great deflection that causes disorder of the spiral spring that lose the electricity and get spoiled, and the coil gets hot and may get spoiled, because in this case the increases temperature of galvanometer and get spoiled. Number 3, the sensitive coil galvanometer should be calibrated after using it for some of the time, because weakness of both of torsion of the two spiral spring and the strength of used magnet which may affect the accuracy of the instrument. The current direction. During the rotation of the coil, a torsion is produced in the spiral spring against the torque acting on the coil, the galvanometer, and increases as a pointer deflection angle increases. Okay, during the rotation of the coil, torsion is produced in the spiral spring against the torque acting on the coil of galvanometer, and increasing the pointer deflection angle increases during the rotation of coil. Okay, we generated or produced a torsion opposite or against the torque acting on the coil of the galvanometer, and the deflection angle increases. In this case, deflection angle increases. When the torque due to the magnetic force balance the torsion of the spiral spring, the pointer stop at the certain reading or the certain value. If the current direction is reversed in the coil, then the coil and the pointer move in the opposite direction. If the current direction is reversed in the coil, then the coil and the pointer moving in the opposite direction.